I'm Josh, also known as Monk. Been coding for like 12 to 14 years. I tend to get easily bored. I like to break things. I like to embed things. I really like to repurpose things. Soldering, assembly. You can find me in any of those places. Probably best place is actually Twitter.
All right. I'm Stoker, and I've been a software engineer for 5 years. Just learned Android about 2 years ago and started really getting into it, as well as like some kernel hacking, custom ROM, stuff like that. I got into poking at the Linux kernel, starting with Android, starting porting things over to Android devices from Linux. I like to tinker with network protocols, see what's going on, see what kind of security vulnerabilities there are. And I like to manipulate gadgets because, Android devices, they have certain features that are locked out either at the kernel level or the driver level. I like to re-enable those features. So you can find me at my MITRE address. MITRE is a federally funded research development center in the States, or just hit my Gmail.
So the project in general that we're going to talk about today was originally and still funded by MITRE. Like Jeff said, they're a federally funded research and development institution. I used to work there, started the project with Jeff. Jeff is still leading it. Oliver and Sheldon are both also working on the project currently. The project has been open sourced. We have a lot of developers that are or have never been at MITRE that are already working on the project, and we're basically just here to explain how mesh networks work, what can be done with them, and show you how much fun it would be to play with them. I guess before we go any further, we need to do the caveat that I don't speak for MITRE, and none of my opinions or anything I say should be taken as MITRE dogma. Is that fair?
Yeah, that's fair.
Okay.
So I also want to give the disclaimer that this work currently is open source. Part of the security effort, it's still MITRE internal, but we're going to talk about it at a high level, hopefully get some feedback from you guys. Those slides have a little disclaimer at the bottom. Otherwise, we definitely want the open source community to take a look at this stuff and hopefully do some custom development on it.
Fair enough. All right. We are one of a handful of groups that are pushing mesh networks. Most of the groups are open source. Here's a list of us and what we're built on and some of the other projects that are also in the same space. One thing we've always tried to do with SPAN in general is give people an option, but mostly we want mesh technology to take off. I don't think either of us care if it's SPAN that takes off or another one. We just want the overall tech to actually get picked up by the community. We think it's really cool. We like our solution, which is why we work on it in our spare time. But, the more important message is mesh is really, really cool, really useful. We want to see adoption. So.
Only other thing worth mentioning on this slide is we are leveraging a lot of open source projects. This is a huge collaborative effort.
Your general, let's finally get things started. This is what we're going to talk about today. First, mesh, just what the hell is it and why should you care at all? Move into how it works. Jeff's going to dive pretty deep into the kernel mods and framework hacks that we're doing. I'll probably talk about routing and why it's difficult. Jeff will talk about security for the mesh. And then if we have time, we'll talk about where we're kind of taking the project moving forward and some fun projects. We'll end with a nice little story if we have time for use cases. So mesh networking in general, how does it work? As an ex-math guy, I kind of like this. It's graph theory. It's applied academic graph theory. The only difference between that and a textbook graph problem is your nodes move and all of your vertices are very, very, very unstable. And, well, the pics are horrendously ugly. But, I mean, conceptually, it's just basic graph theory 101 until you start trying to route through it, which we'll get to later. So in a nutshell, we're hijacking Android phones to enable a mesh over the Wi-Fi chips. Every phone talks to every other phone that it can reach via Wi-Fi in a peer-to-peer way. And now to get into the impetus of why we care. So this happens over the world, and it really, really, really sucks. I'll just try to make this easier. First, Katrina happened, and 3 million landlines go down. Basically, Katrina rolled in. It wiped a whole city's ability to communicate just off the map. I mean, there were bigger problems than not being able to make a phone call during Katrina, but not being able to make a phone call was also really, really bad, and it kept people from being able to call and say, I need help now. That's cool. No one uses landlines anymore, right? We're going to use cell towers instead. Well, in 2000, cell towers knocked out. That's basically most of New Orleans. NOLA just had no connectivity. The plan was to back up to radio. Radio started dying and was horribly, horribly degraded as well. We actually got in the position where typical home ham radio operators were neighborhood-based, calling into 911 to actually report ground truth to the police because that was the only insight they had. You also had field reporters from like CNN and the other big news agencies coming in, and they were actually might as well have been 911 dispatch operators. I mean, all of our infrastructure that we believe and rely on and just take for granted just went away in a couple of hours, and we saw everyone flailing to try to recoup from that. And it wasn't pretty, but that was 2005. We learned our lesson, right? So Haiti, 5 years later, 2 main phone providers, both down. Cell networks, down. Fiber optic, down. The odd thing about Haiti was it wasn't actually the earthquake that killed most of the infrastructure. Infrastructure survived. Yay. A lot of humanitarian aid from across the world went down to Haiti to help because they really needed bodies to help. The influx of cell phones killed the network. So it wasn't actually the earthquake. It was all the volunteers that brought it down trying to help. But, we're getting better, right? Japan had an interesting solution when it came to the earthquake. At a provider level, they just shut off cell access to individuals, basically. I mean, 90 to 95% of the service was limited. Basically, if you weren't an emergency service provider, your phone just wasn't going to work. That did keep the emergency service providers up and running and able to communicate, which, is, I guess, problem number one. But it left a ton of families wanting to tell each other they were okay, that they couldn't. So we have, 7 years now of believing we can trust an infrastructure that we use every day with our shiny cell phones that is very fragile and fails. These are the big examples, but if you start digging through news articles, you can find smaller, more spot examples across the world where the infrastructure just gets overloaded and dies. Infrastructure is also fragile to worldwide events that are not natural disasters. Arab Spring would be the easiest one to kind of talk about as an impetus for why this project is interesting. They just decided they didn't want people using Twitter or SMS to collaborate and get in groups for protests. So to combat that, they flipped a switch, and now there was no internet for cell phones, right? Hurricane Sandy, if you followed any of that news, if you lived around New York, it was very interesting because most of the infrastructure for news media went down except for Twitter. We tend to rely more and more and more on these things to get our information across and to talk and communicate. And so that infrastructure, be it fragile from just global events or from nation states wanting to insert control over it, is something that we don't really love. You saw a lot of cell communication, especially in the last Palestine and anonymous kind of interactions there. There was a lot of push for using Twitter and other pseudo non-trackable social media to get people together. And again, it's all based on a fragile infrastructure. So our solution, everyone carries one. Let's make an army of Android phones.
Army of Androids can solve all the world's problems.
They can, and they're awesome. So in general, everyone has a phone in their pocket. That phone can do a lot more than just phone calls. We already know that. What can it do? Well, the one thing we can do is we can grab control of the wireless chip in it, and we can start creating a point-to-point network between all the phones. We can scale this very large, larger than we've been able to test. But basically, we can provide an infrastructureless system for communications. We don't really rely. We can prove that there's not always a need for a cellular infrastructure. Cell towers aren't required for communication. Active Wi-Fi networks aren't really required for communication anymore. We can get by maybe in limp mode, but we can still provide the ability to communicate across a group solely with the phones. And at the heart of it, that's what SPAN is. The other interesting thing we can do, because we control the phone at such a low level, we can start bridging between the various parts inside the phone. So if I have a fully spun up mesh network using Wi-Fi and a handful of phones still have broadband access via their baseband chip, we can bridge those. So we can share the internet through the internal network by basically making phones bridges and gateways. Next slide. And just a nice pic to prove it happens. Here's our app running on a handful of phones. Jeff's got a whole bunch of devices up here if anyone wants to play with it afterwards, but that's where we are right now.
The one thing I want to mention here is there's an alpha USB dongle attached to that Asus Transformer Prime tablet. It's using that alpha dongle to connect to a wireless network. It's also part of the mesh network, so there are two wireless interfaces, and it's bridging the two. We don't actually rely on the alpha dongle at all.
I think you're up now.
All right, so the idea here is there's many projects working in this space, and everybody has to start from scratch, it seems. So with the SPAN project, we wanted to develop a platform, a framework, so that academia as well as just interested open source developers could just jump in and start making their own mesh network and writing their own mesh-enabled applications. So it's all pushed to GitHub. We'll give you the link later. The hope is that we made this as simple as possible for people to just integrate it or use it as a basis for their future work. So here we have a picture, and what it really shows you is that the mesh is just a transparent backend. It's designed to work just like when you're connected to your access point or cell network. Imagine that you're at home, right? And you have your Facebook app up and running, and you're connected to your home wireless AP. You walk outside, you're outside the range of your AP, now you're connected to the cell. Facebook app still works. It doesn't care what your network backend is. What if you go outside the range of your cell? Why can't you jump on a mesh network? And that's one of the main things we want to do with SPAN is make it that simple. Make it a third option. So what this is showing you here is that we can set up a transparent proxy on these Android devices that intercepts all outgoing communications and incoming communications, and it routes them through a reliable transmission layer, reliable UDP. And we can also, in our internal layer, route them to the next hop in the mesh. Because in a true mesh network, you can connect to somebody directly peer-to-peer, but the true value of it is you can hop through your peers to get further distances across the mesh network. And those hops are controlled by the routing protocol. You need to decide who you want to hop through next to get to your end destination. So this transparent backend is developed such that when you write an application to work with the mesh network, you just open up a UDP socket, TCP socket, and it works. There's no custom mesh API, and that's one of the things that differentiates us from other open source projects. All right, so the stack. A lot of this is still conceptual. Some of it is actually implemented. What you see here are your apps at the top. Use your standard, Java networking interface through, standard Java code, got your UDP, TCP sockets. The idea here is your apps use these sockets as per normal. Data gets routed through a transparent proxy back to these internal layers for reliable transmission. We have a layer here where we support various routing protocols. Whether they're proactive or reactive, we'll explain the difference. And down at the bottom, the routing protocols modify the internal routing tables. So we use tools like IP tables and NetFilter to make that happen. So that's it in a nutshell. All right, so easy problems that are in fact hard. Wouldn't it be great if Android just supported ad hoc mode? Well, it doesn't. So, problem number 1, wireless chip. What wireless chips support ad hoc mode? Which ones are easy to work with? I don't want to say Broadcom is awesome, but Broadcom works very well for us. And Broadcom is a wireless chip in most mobile devices these days. So the devices there on my left are ones that I've taken a look at. We support the Nexus S4G, the Galaxy Tab 10.1, some other Samsung devices. We don't support the Motorola Razr Max. One of the reasons we don't support it yet, with some extra time we probably could, because it uses a Texas Instruments wireless chip. So it requires a different technique. But we definitely think we can support the Nokia and the iPhone 5 because they also use Broadcom chips, just like many of the Android devices we support. All right, so ad hoc mode on Android. In addition to the chip supporting ad hoc mode, the kernel itself needs to support wireless extensions. And it's kind of a mixed bag here. Some devices support wireless extensions, others don't. Some have the right chip, others don't. Some have the right modifications to the chip drivers, others don't. So it's kind of something that requires some taking a look at and requires a custom kernel for a lot of devices. All right, so custom kernel mods. What we're doing to set the device in ad hoc mode is just using iwconfig. Anybody who's familiar with Linux knows what that is. And in order to use iwconfig, we need to support wireless extensions on the device. In the future, we want to move away from iwconfig. It's kind of old hat now. The modern wireless APIs for Linux are Netlink, which are rolled into a lot of the new Android devices. Don't have full support for ad hoc mode at this time, but in the future, we'd like to start using IW instead of iwconfig. All right, so here's some code. What changes did we actually make? For the Samsung Galaxy S3 International, it's just these few things. So you see there in the make file what we've done. See if I can use this. All right, so in this make file, all we've done is taken out this option, and that was really it. We just removed this. And what this option does is it filters out UDP packets on the device when the screen is off. It does that to save some power. So in a mesh network with a proactive protocol on a device, the device constantly chirps, says, hey, I'm alive, hey, I'm alive. And if your screen is off and you're not able to hear that chirp, you don't know who else is on the mesh. You kind of isolate yourself. So we got to remove that option so you continue to hear those chirps and know what your mesh looks like. All right, so there's also this other file in the Broadcom DCD wireless driver code. All I've done is add this part here. What this is, this interface modes, that's just a list of your supported wireless modes. There's manage mode, like infrastructure mode, where you connect to your access point. That's what your device typically operates in. There's like monitor mode, and there's another mode called ad hoc mode. All I did is I just ordered that extra bit in the list. Now it supports ad hoc mode. It seems like this has been purposefully removed from the code, possibly to prevent people from tethering their devices to their cell network. And you can understand carriers want to stop you from doing that so that you don't take advantage of your unlimited data plan or any of your other carrier services. So this is really simple. This has nothing to do with wireless extensions, but just wanted to show you how simple it can be. All right, so sharing span. One of the big things is disaster happens. You got this phone in your pocket. It's more than a brick. Let's say somebody was smart enough to ahead of time have installed SPAN app on their phone. Or maybe they're connected to a computer with a SPAN app on it and they can ADB install it. So now one person has the app. You still need to share that with all your friends. Maybe they never even heard of SPAN. How do you do that? Well, Android does not make it easy for you to share an app with a friend because you can pay for an app, download it, and then share it with your friend. They don't have to pay for it. So what they do is they filter out the APK extension when you try to share something via Bluetooth. All right, so Bluetooth's out. NFC. You can share whatever you want using NFC, but there's really no built-in NFC app to do the sharing in most off-the-shelf Android devices. If you're smart enough to have downloaded that app ahead of time, use it. But most people don't have the foresight to do that. All right, so what we actually do is we leverage this from Robble, which is another mesh project for Android devices. What we do is we turn your phone into an access point. We actually flip it into master mode, and now another device can connect to it, just like you connect to an access point at home. And we run a little web server. And now when a device is connected to your phone, they browse to your server page, and they download the APKs directly from there. So now you have SPAN installed, and they have SPAN installed. Last thing worth mentioning here is that in a mesh network, you need to share the SSID, the shared key, the channel information, other sorts of things with other people so they can all jump on the same mesh. We share that info, that config file, using Android Beam. I might say bump because I like to think about phones bumping. I know there's a bump app, but that's not what I'm talking about. You can actually share that information by physically, NFCing it over. All right, hard problems that are in fact hard. Ad hoc mode on iOS. Now we do have some iOS support currently. We can get an iPhone to work in our mesh network, but it acts as kind of a ad hoc relay. It can't originate the ad hoc network, but it can connect to an existing one. An Android device can actually set up the ad hoc network so other devices can see it. An iOS device can't do that. It would require some finagling with the private framework calls, possibly some REing of stuff. It's a difficult problem. We're interested in pursuing it. Don't have it working yet.
All right. Am I on? I think I'm on. Yeah, I'm on. Okay. Mesh routing. Mesh routing tends to be a very hard problem because we've had computers networked for a long time. We're used to how they work. We're used to thinking about how networks work in a wired environment. And most of that has to be thrown away or at least heavily reconsidered when you're dealing with a mesh, especially a mobile ad hoc mesh. It just seems to be an incredibly difficult problem. The two big takeaways really here are there's some main players in mesh routing currently. There's OLSR, which has been around for 5, 6, 7 years now. They've been around for a while. And then there's Batman, which is a better implementation of OLSR. If you start Googling, those are the two kind of main things you'll find. But the whole scope pretty much breaks down into two mentalities, proactive and reactive routing. In a proactive mindset, you're kind of in your more familiar networking ground, right? I go out beforehand, I kind of scan the network, I kind of have an idea of what the topology is, and I can start planning routes. I know that if I need to get to Google, I hit this computer and then that packet needs to jump through this device and that device and that device. And you kind of have a pre-planned route to an extent. In implementation, that gets thrown away a little bit, but it's the mindset is kind of a Boy Scout mindset of always be prepared, know what you're going to do firsthand. Reactive routing, on the other hand, is just the assumption that I'm not going to have any idea what my topology is going to be in this mesh. It's too dynamic, it changes too fast to spend any time actually trying to figure out what's going on. I'm going to lazily wait until I have a packet to send, and then I'm going to start basically asking everyone around me, all my friends, hey, can you get this packet here? Can you get this packet here? And, that's very generalized, but that's kind of how the two mentalities work. I don't really want to spend a ton of time on the details if we don't have to, but please ask because it's what I geek about. There is a new spec coming down the pipe. It's not here yet. It seems to be fairly far off. We're hoping to see this slowly become adopted. If it does and actually becomes more mainstream, we will definitely jump on it. We're hoping that a lot of the new work in Ubuntu will push this through so we can start grabbing it. But it is probably at least a couple of years off from reality as far as getting it in a functional mesh.
All right, security. It's never too early, but it's always too late. All right, authentication. Okay, in a wired network, you have a CA. In a mesh network, you don't want any servers because that server node can leave at will. Then what do? You can assign another server node. That gets a little bit out of hand. Can we get away with not having servers in a mesh network? That's a more interesting question. So what we do is we use something called Tink, which is an open source project. It stands for This Is Not Cabal. Cabal is another word for Big Brother. And basically it runs a little daemon on each of the nodes. And you can use public-private key security to set up VPN links directly from one node to another. And you can, because the information is encapsulated in a VPN packet, you can hop that across other people in your mesh without a problem. They can't look in your packet, your crypto is good. So then the question is, how do you share these keys? There's no CA. You can't just query the CA, grab a key. Well, there's really no good way to do this in a mesh network. The way we do it is we either allow the users to sideload the keys on their device, and then they have them, or when you run span for the first time, we generate a key, and you share that with your peers using NFC. Physically, in person, you see them, you authenticate them by looking at them, you share your key. Now, I share my key with Stoker, Monk, I share my key with Monk, and then he goes off and he meets somebody else. Now, he can share my key with that other person. So now these keys kind of proliferate throughout the entire network by actually physically meeting people. And when you share a key with a new person, they have the option to reject it or accept it. So, it's a very transparent system. There's really nothing going on behind the scenes. People know whose keys they have, and they can reject a key if somebody tries to pass them one and they don't really trust that person. One thing I want to point out here is you can't share public keys over the open air without doing proper authentication, because I can be like, okay, here, Monk, here's my public key. And Monk's like, okay, I think that's Stoker. Maybe. Okay. So, if you don't have any pre-shared information, there's no way to do authentication. You shouldn't share keys over the open air. All right. Strategic fallback. This is kind of the idea I hinted on already. If you have a certificate authority and you have certificates, if you're part of a big organization like FEMA, hey, just load those keys on your device, with the root CA keys, and then you can validate signatures and do all that great stuff. All right, you don't have a CA? Generate a key on the device, share that instead. All right, you want to talk to somebody who you never met in person. You want to talk to somebody for whom you don't have a key yet. In order to even get on the mesh, you have to have a shared key. We don't want people hiding in the brush, looking at the mesh network and saying, oh, free mesh, I'll jump on and I'll maliciously modify these routing packets so everybody routes their data to me, and I'm just going to drop it on the floor. So to prevent denial of service attacks like that, we force at least a shared key for everybody in the mesh, and there's at least a minimum level of encryption going on. All right, so this presents an interesting concept where, let's say there's node A and he meets node B in person and they share their keys. All right, that's trust level 1. They've seen each other in person. They know they can trust one another. They know who they're really talking to. Well, I share my key with Monk and he shares it with somebody else. Now, that other person that Monk met, I can grab his public key through my VPN link with Monk. I can securely grab that key through that VPN link, but I've never met that person whose key I'm grabbing. So that's kind of a trust level 2, because I've never actually seen that person. You can keep going through more and more trust levels based on how long your chain is. And the reason these trust levels are important is because let's say you want to do a group broadcast, but you don't want a malicious entity who might be in your network to get that message. So maybe you only broadcast to trust levels 1 and 2, or maybe only trust level 1. You can also promote trust. So here at the bottom, you can A promote C, and so now the link between A and C instead of 2 is a 1. now all of the trust levels that A got through C get promoted as well. So it takes a little bit of monitoring. You can set this up to be automated, but the idea is to make this known to the user. See how much risk he wants to assume.
Cool. All right. This is the first slide that we're going to talk about new technology that we're currently very much in preliminary stages of working on. You're not going to find Mercedes in GitHub right now. I'm actively trying to secure funding and actually get the code starting to roll out. So the concept of Mercedes in general is you have this wonderful big wireless mesh, and you want to have communications. Maybe you have crypto, maybe you don't. But you want to make sure that you have unsniffable comms. In typical networking like we have now, that's hard. You have things like Tor that give you some anonymity once you get into that network. But those first couple of hops from, my home router into another Tor node, I normally don't have much choice of where those go. Like, my anonymity starts at some point online 3 or 4 hops from me. And that's about as good as I'm going to get. What Mercedes says is, I want to flip into Mercedes mode on my phone and do all my routing that way. So when that happens, my phone makes a topological map of the whole wireless mesh. And then I do an analysis of that from like a simple graph theory standpoint. And I find out exactly how many unique paths I have through that whole mesh from point A to B. So instead of just finding the optimal route like you normally would, I try to find all of the routes. So I have 10 unique routes I can pass data through the mesh. I'm going to take every single data packet that I have to send, cut it up into 10 equal-sized chunks, and send those on 10 disparate paths. That way, if any single person is on the mesh or any subset of the entire mesh is compromised in trying to sniff traffic, it becomes irrelevant. At best, they get a part of a packet. The only way that you could fully do a man-in-the-middle attack or any sort of just eavesdropping on a conversation would be if you controlled every single node on the mesh except for point A and point B. In a nutshell, that's Mercedes. It is just trying to take the anti-sniffing game to the complete next level. And it's a toy that we can play with in meshes. It's a toy we can play with in other networking infrastructures aside from our typical internet, where we don't have just a single path into the net.
All right. The one thing I wanted to add, this is all Monk's work, but I wanted to add that you divide the packet into 10 equal parts. You can actually take each of those parts and duplicate it and send them over multiple routes. So now if somebody's on one of the routes and dropping all packets, at least you have that packet duplicated going down a different route as well. So it's more guaranteed to get to its destination. All right, so the real world. Yes, we have tested this in the real world, and how does it work? All right, so these aren't scientific numbers. We have yet to actually get out our true measuring equipment and do this. But usually the max range, device-to-device, direct link, using 802.11g, channel 1, 32 dBms, a little bit over a watt, which is the max these phones support. The range is about 500 feet, which isn't too bad. I mean, it's way better than Bluetooth, but that's what you get. So the idea is add more people to your mesh so you can hop. Considerations in the future, there's going to be a technology called LTE Direct coming out. You guys know what LTE is. LTE Direct is a peer-to-peer form of that. So using the LTE chip, talk directly person to person. Now, when that's released, hopefully in 2015, you should be able to talk distances of, they state 1,640 feet. So that'd be great to use just to get longer distances. Problem is, LTE probably uses some proprietary spectrum owned by your carrier. There is a first responder band being used in the States. I think it's like 700 megahertz. We might be able to make use of that. All right, so throughput. All right, on the Galaxy Nexus, The throughput was 13.3, megabits per second. Get a little bit more with UDP. Nexus 7 was actually much better, 30.6 megabits per sec. Why is there a difference? Because they use different wireless chips. Nexus 7 uses a little bit more modern Broadcom chip than the Galaxy Nexus. So I threw up this nice little graph here, this little chart. You see where span fits in the mix between Wi-Fi and WiMAX. Can speak on the edge of the longer edge of the Wi-Fi range, lower edge of the Wi-Fi throughput. All right, what can we actually do in the mesh? Here are some apps. If you want to come up afterwards, I can show you them in action. Get this really simple app based on Wi-Fi tether for root users. Turn on the mesh. Bam. Hit that big, originally gray icon in the middle with your thumb after you configured SSID and IP. And now you're on the mesh. We actually have a visualizer. You get a nice node graph to see who else is in the mesh. We also implemented a voice chat app. So you can actually have your own little, short-range walkie-talkie. It's not true VoIP, but it's proof of concept to show that, hey, you can actually get comms directly over an ad hoc mesh network. And you can also set up teams of people so you can chat with multiple people at once. All right, so future work. Josh is going to talk about his Mabel stuff. I'm going to talk about CAMP. He already talked about Mercedes. We want to leverage the Open 802.11s work when that comes out. We want to get true VoIP support. Serval, another project, has already done a lot of that. It'd be great to implement their daemon into our framework because we want to support a variety of routing protocols. Delay-tolerant networking we'll discuss in a moment. Big problem here is there's no DHCP server. So how do you get a unique IP address? Well, using IPv6, you can use link local addressing to generate a unique IP based on your Mac. Problem solved. We want to support iOS, Windows 8, BlackBerry 10. That's in the works. Android is what we currently support. LTE Direct I already talked about. Generate some span ROMs to make it very simple for user installation.
So, Mabel, this is another project I'm currently working on. One of the intriguing things about a mesh is it gives the ability, for people to communicate. Let's look at an Arab Spring situation where you no longer have communication to the outside world, but you're still sharing information internally into the network. That's great. Let's say you do want to try to funnel that out to the outside world at some point. Or you aren't Arab Spring, you're some soldiers deployed somewhere, you're collecting information and you're trying to get that back home to base. Anywhere where you're out collecting a bunch of data. We have, the phones we carry are pretty easily damaged, and it's horrible to see a lot of valuable information that we would like to get out in the public die when a phone dies. So the intrigue of Mabel in general is just, we have a distributed peer-to-peer network. Let's lay the BitTorrent protocol on top of it. What does that do? That lets me basically treat my whole network as one big-ass RAID 5. I can distribute any data that I have on my phone across the whole mesh and make sure that anything I care about is redundant. And that way, any single device that is compromised or taken offline doesn't affect the data of the masses at whole. It's a beginning glance at looking at this type of network as an organic entity with a memory. So you can start adding information to the mesh, and not only does it distribute to people in real time, but it also kind of backs up in the same way. That is Mabel in a nutshell, which is a good intro for CAMP.
All right, so CAMP stands for Computing Across Mobile Phones. So essentially, you have all these phones together in a mesh. What can you do with it? Why not leverage the combined computing resources in the mesh to do some distributed processing? So you guys might know about SETI at home, folding at home. These are like massively distributed processes for, folding protein, genes, and trying to come up with a cure for cancer and other things like that. So the idea is, if you have all these smartphones together in a mesh, let's say you have a really computationally intense algorithm you want to run. Maybe you want to do some, object recognition in full motion video. Somebody took video over a period of time, and now you want to be able to scrape through it for things of interest, maybe people who are suspicious or certain things that are just out of place, maybe trying to do bomb spotting or whatever. That is a very complex process, and it's going to eat up a lot of resources if you just run it on one device, and it might take a very long time. Why not distribute it across the mesh so every device in the mesh has a subtask, and they can, churn their own part, and then you aggregate the results, and now you have your solution. So there are some other applications as well. Like maybe there's a structure, and you have your whole group of friends, and you all take a picture of it from a unique angle. You can do something called three-dimensional reconstruction, where you create a three-dimensional model of that thing. That's also very computationally complex. Another example is SPAN is going to be used by these folks at MITRE who have these basically remote-controlled Tonka trucks. And each of those trucks has an Android device attached to it, which is controlling its wheels and sensors. They deploy these trucks out in a football field to take heat readings from the stadium lights. And they deployed 10 of them, and they all worked together as a big group to take readings in various regions of the field, the football field, and at the end they combined it together to create a three-dimensional heat map of the entire field. You can also use this for investigating unknown territory, creating a 3D map of the area. So having Android devices or any mobile devices connect together in a mesh to do distributed computing has a lot of different applications, and that's something we want to be pursuing in the future, especially since there's Tegra chips now that have a high number of GPUs and CPUs available, and most applications never even make use of them. So you can do parallel processing on a single device as well as distributing subtasks among multiple devices. All right, so that's CAMP, virtual supercomputer over a mesh network.
So, and this is the last kind of forward project we have that we'll talk about. And the idea actually started as a joke. There was an old RFP for IP over carrier pigeon, which is kind of where this started, and it rolled from there. But it was, what if we could figure out a way to make data itself geo-resident? So right now when I go somewhere and I pull my phone out and I, go on Yelp to try to find out where the closest restaurant is to me, or, where the closest person giving speeding tickets is to me, I have to go hit a server. What if with the transit, we have people moving in and out of locations all the time. If I could basically label this data itself as this exists at this lat long, so any device that's on the mesh that comes near that lat long now contains that data and will pass it along to anyone else. You're basically, with the transitory way of how a mesh works and how quickly it moves, you're able to lock data itself into a position. So when you get near it, you've basically broken a geofence, and now you can be alerted about something. Something as lame as advertising for, hey, buy this stupid product, or something as interesting as I'm driving an ambulance to a hospital, and that hospital is now completely filled with no beds in an emergency. I need to reroute somewhere else. In that situation, I have no internet. So it would be awesome to get that information as me, the ambulance driver, is driving with a route to where I should take that patient in the back instead. And all of these technologies are basically built on a solid core mesh network, which we believe we have working to some extent. And we think in general it's a project that Jeff and I both really believe in and think that it can move forward. What we need is just people that are interested and want to tinker. Not a lifelong commitment to bang on this stuff, but anyone that spends 10 minutes playing with us and just tells us if it works on their phone or not saves us days and the cost of buying your phone to see if it works on your phone. Android in general is difficult to develop on when you're customizing for hardware. It's very difficult to get one instance of every piece of hardware simply to test on. So if you're interested at all, that's a great way to help out. Just download the app and tell us if it works. That is literally 10 minutes of your life in an email to one of us.
So one thing worth noting is that the apps are posted on Google Play. Make sure to read the description for the man-aid manager because it only works on certain devices. Other devices it works on if you install the custom kernel that's posted on GitHub through Clockwork Mod Recovery.
Yes, we're out of time. I'll tell the story in 10 seconds. So we were asked last year to go support the Major League All-Star baseball game. In the States, it's kind of a big thing. Basically, Kansas City is a small city. I forget how many people it has, but it's not a ton. The influx for this baseball game is about 75,000 people. So the powers that be were expecting that the cell networks would die because you have a huge influx into a situation that just normally can't support that many people. Oh, wow. That's scary. So, I mean, in general, the Kansas City brought us out to say, hey, we're expecting the cell networks to die. And I guess one thing we never really got into because we were rushing for time a little bit was infrastructure around the world is generally built to sustain about 80 to 95% of everyone that lives in that geographic region picking up their cell phone and making a call. If you have 100% of the people in Amsterdam pick up their phone and make a call right now, the infrastructure will die. There is no cost benefit to the providers to be able to handle more than 95%. It's raw, sheer numbers, profit business. So when you have an influx like this where chances are you're adding a 20% bump on top of your normal populace for a day, and especially a day where everyone's going to be taking pictures and tweeting and sending SMS and email and stuff, they were expecting the network to die. So they kind of contacted us and were like, hey, do you want to do a science experiment with live humans? And we were kind of like, yeah, that'd be awesome. And what we were there in general for was, let's support the police department. They're also on this network. Let's make sure the police department has a backup in case everything dies. When we rolled out there, AT&T and Sprint and Verizon, which were the big players in the States, were also out there spinning up secondary networks because they knew that they would die otherwise. And everyone ended up surviving. We had a good science experiment that basically proved that a mesh is viable, especially in a highly dense audience. But we took some fun pictures that are always kind of funny to lulz at. So the first one is just what Jeff and I's hotels typically look like when we go out. So you're rolling somewhere and you've got 50 or 60 cell phones that you're going to hand out to people. Charging them in a hotel is a pain. It's hard. Each one of those things dinged all night long to let me know it was charging. Actually, what was even worse is the 24-port hubs that we had that we were charging, the wattage and amperage on them could only actually charge 5 phones at a time. So the first 5 would charge, and then those would start decharging to actually charge the next 5. So they would ding when they were complete and then ding when they were fully discharged, and it was just this circle all night long. But we finally ended up having, I don't know, we slept in stages solely just to charge phones, which was pathetic. And so then the day we go out to actually do the install and test our network in the real world, we realized there were a couple places around the stadium that just weren't going to be dense with people. And as engineers at heart, we were like, well, how do we solve this? We have extra phones. We have batteries. We have plastic baggies and duct tape. Let's put the phones and the batteries in the plastic baggies and then duct tape them to a tree. So that's our other cohort, Nick, actually crawling up in trees and duct taping phones. The problem with this picture is we were specifically there to support the police, which were worried about terrorists and terrorist activities at the stadium. So random people crawling up in trees and duct taping quirky electronics. I think out of all of these suspicious activity reports that the police had, which I think was 11 for that day, we were 6 or 7 of them. So they were both thankful and very, very angry at us at the end of the day, in a fun way. But it was a good experiment, and it did prove that SPAN is viable for these type of situations. Go ahead.
All right. So don't have that much time left, but I do want to give a shout out to some other projects. All right, so at Mobile World Congress this year, Ubuntu Touch was something that was talked about. And it looks pretty flashy. I can't wait to play with it myself. We think that Open802.11s is going to make it to this device. Sadly, Ubuntu adoption among non-geeks might be a little bit low. Hopefully not. I'd love for everybody to jump on it and use it. But if it's low, the idea is port some of that stuff over to Android. So then, typical people can install it through an app. Commotion is another mesh project currently out there. It's being led by the Open Technology Institute. It's collaborating among multiple people. They're responsible for the OpenWRT firmware stack for routers, which runs OLSR, which stands for Optimized Link State Relay. It's a routing protocol. SPAN supports the same routing protocol, so we can talk to those routers. Serval is another big project out there focused on letting people make phone calls using a mesh network in the same way they would make a phone call when using a cell network. They have their stuff wrapped up in a nice little daemon we'd like to integrate into a SPAN as well. Thing about their stuff is pretty much a reimplementation of the network stack and user space, which is an interesting idea. It has some pros and cons, and I can talk about those offline. Freifunk, considering that we are in Europe, you guys might be familiar with this. It's German for free radio. They have about 500 mesh nodes set up in Berlin. It covers the whole city, and I hear it works very well. They're also using OLSR and OpenWRT firmware. Byzantium is kind of a buzzword these days. These guys are writing their own Linux distro for x86 architecture devices. So not Android, but Windows machines and what have you. The idea is they use the Babel and Batman Advanced routing. Batman Advanced is a layer 2. We'd love to also integrate those into SPAN as well. SPAN is a platform that we hope will be routing protocol agnostic, so we can play nice in a sandbox with the rest of these projects. So what makes SPAN unique? This is an important slide. Keep calm, it just works, right? It's an Apple thing, but the idea here is that got Wi-Fi, use it. Got cell, use it. Don't have either, use AdHoc. Apps will just work. Just use a socket. No special API necessary. We do provide an API if you want to get the peer list and write mesh-enabled applications for like voice chat or text messaging. We support multiple routing protocols. That's the hope. And our team is not afraid to mess with the kernel. A lot of these other teams, they say, we don't want to touch the kernel. We just hope that in the future, Google adopts AdHoc mode into the AOSP. That work is ongoing with Google, but currently we provide custom kernels for those who want to work with a mesh network now.
I think we actually like working in the kernel. I don't like user space.
True. So, all right, this presentation will be up on GitHub under Monk's account. The actual code is right there. You can go browse it right now. And we got another link down there at the bottom for Monk's domain.
That's it. If you have any questions, please grab us.
All right. Are there any questions right now? So everybody's good. All right. Oh, you, sir.
You mentioned one of the issues you were charging the batteries for the phones and all that, and knowing wireless drains a lot of batteries. You guys are looking into helping that situation where the wireless drains less batteries?
We have seen, I think the first couple phones we got working in a mesh, the batteries lasted like an hour or something. I mean, they died pretty quickly.
A little bit better.
We've made significant progress, and I think the last testing I did, non-scientific testing, just kind of from the gut, we were able to get about 85% to 90% of normal kind of battery longevity like you're used to. So the impact is still there, but it's going away. I've looked into writing a custom routing protocol that's basically solely based on optimizing the battery. Whereas I think that protocol in and of itself would be useless. I think the research would turn around and help the other routing protocols actually do good things. But we just haven't had the cycles. Once we got it up to, kind of feeling like acceptable limits, we started focusing on other problems right now.
I'll just add a little bit more there. We did do some tests. We actually hooked those batteries you saw in the picture hooked one of those up to a Galaxy Nexus. It lasted 14 hours, but we did that test with GPS off and screen off. In a proactive protocol, the thing constantly chirps. That's kind of what's eating up part of your battery. So if we use a reactive protocol that kind of remains silent until you need to actually send data, it won't be chirping at all. And I think that'll save us a lot of energy at the cost of delaying message transmission until a route has been planned. Any other questions? Yes.
Everyone is using reactive routing protocol. What would that be impact if someone wants to stop transmission? No one knows anything about
to try to simplify it, to answer it quickly, right? So what's going to happen is if I realize I need to send a message, I'm just going to say, I need to send a message, and hopefully someone's going to hear me, right? And that person will turn around and go, hey, he needs to send a message. And it's basically a broadcast out for anyone that can hear you kind of chain.
Right. So
it's actually in implementation, it's slightly better than that. But I mean, kind of the dumb way to explain it is, it's just broadcast.
So there's going to be a delay. So depending on how far away your destination node is, the broadcast is going to have to be propagated that number of hops. If it's very far away, it's going to take a long time. If it's closer, it's not going to take as much time at all. Any other questions? All right, guys, feel free to stop up and take a look at the app if you want.
Thank you.